It's very nice here. So I want to tell about some mostly conjecturally approach using mirror symmetry to study geometry of algebraic varieties. So very briefly, mirror symmetry is just the theory about duality of algebraic and symplectic properties on different varieties. So it came from physics in late 18th, I think, and from the mathematical view, it has some there is several conjectures of mirror symmetry closely related, but the main of them, I think, the main. I want to talk about using two of them. One, so. One of them is homological mirror symmetry. Mirror symmetry, or just HMS, which is due to Kontsevich. It's the most deeply developed type of mirror symmetry conjectures, and contains a lot of information about geometry and so on. But disadvantages, it has a disadvantage. It's, well, if something contains a lot of information, it's usually hard to prove this conjecture in a lot of cases. But I don't want to describe it, but I just said that it states duality in terms of derived categories. I'll tell maybe more later, maybe a bit. So, in terms of derived categories. I want mostly to talk about another conjecture. It's much easier, but well, and of course, because of this contains less information, but we suggest that they should give the same result. So I will use the second type of mirror symmetry conjecture to find for finding dual variety to our variety we want to study, and just given the result to make predictions using this homological mirror symmetry. So anyway, it's mirror symmetry. It's called mirror symmetry of Hodge structures variations. And now I briefly describe this conjecture, and in simple cases we are interested in this talk. So about mirror symmetry of Hodge structure variations. Let us given smooth find a variety, so anti-canonical class example. That's fun. with Picard number 1. So all devices are proportional. Well, I just want to talk about this case, but most of definitions may be given in the just for much more general case, and we denote its dimension. Of course, everything is over C, and all varieties are projective, and most of them will be smooth. So dimension equals enlarge. So given this variety, we may associate the set of numerical invariants, which is called Gromov-Witten invariance. Then invariance. So it's just numbers of rational curves. So it's we're interested in genus 0 Gromov-Witten invariance. Numbers of rational curves line on our variety and intersecting some homological classes just to be finite number. It's just examples are how many lines pass through 2 points on P2. We know it's only one. Or how many lines pass through point on three-dimensional cubic, it's 6, or just conics intersecting some lines, or just of this type. So Gromov-Witten invariance, numbers of rational curves on X. And of course, it's a lot of such invariants, such numbers, but there's a lot of relations between them. And actually, in simple cases, they may just, the knowledge of all of them may be deduced for knowledge of some finitely many of them, and using the relations we may find all of them in terms of this given basis. I will show it in maybe 5 minutes later. But anyway, these invariants or part basis in some sense in them define the so-called quantum cohomology ring. It's a deformation of ordinary cohomology ring. So as a vector space, it's just polynomials in one variable. One variable means that our Pk number is 1. Polynomials with coefficients in cohomology. So we'll denote the variable t. Deformation means that if we put t equal to 0, we'll get just ordinary cohomology ring, and there is a quantum multiplication. So it's the map from quantum multiplication And that's what we need to formulate our mirror symmetry conjecture. Given this quantum cohomology, we may construct the so-called regularized quantum D-module. Well,
did it form a power series or just?
You can define as you want, but polynomials are enough because, this quantum multiplication is just a formal deformation with structure constants being this Gromf-Witten invariance. But by definition, I hadn't give you a precise definition, but anyway, when you multiply something, you get polynomial, not for fun variety. You get polynomial, it's not power series. So you may define, but polynomials are enough. So regularized quantum D-module. We denote it by Qx. It's just the following. Regularization is combinatorial. Well, it's easy procedure we need for, so it's not important. But quantum D-module is, or differential equation in our case, it's just the following. Consider a fine line with coordinate t, and consider the trivial vector bundle with a fiber with cohomology. Sections of this this trivial vector bundle are just these polynomials or formal power series. The module means that we need to define how to differentiate, so how to use the derivative, how derivative acts on sections. And we say that our connection defining this D-module is just a quantum multiplication on by canonical class. So anyway, I don't want to give precise definition because it's not a point of my talk, but now I will give you example in some easy case. So anyway, there is a procedure how to construct this quantum D-module. So if you know these numbers, this Gromf-Witten invariance, you may construct them in some easy enough way. So is it okay to write here or it's better upper? Okay. Now assume for simplicity that x is quantum minimal. So that's minimal. It's minimal in some in sense of quantum cohomology. So as I've told, to get this construction, we need need only how quantum multiplication on canonical class. So if this there is subreunion quantum cohomology containing canonical class, if it's as minimal as it can, then variety is called quantum minimal. Examples are complete intersections intersections in projective or weighted projective spaces, threefolds, fun of threefolds, and just, for example, Grossmanians are not quantum minimal, they're very far. Quantum multiplication makes this, its cohomology a lot. So now in this case, this simple case, just like for complete intersections of Fano threefolds, mostly we later will be interested in Fano threefolds case. But in this case, this procedure may be simplified in the following easy way, just combinatorial. Write down the matrix, the following matrix with, so it looks like this, then 0, 1, so it's upper triangle and with 1 under the main diagonal and the rest are 0. It's called counting matrix with the following entries. So to be more precise, EIJ. Entries are written in invariance corresponding to quantum multiplication to canonical class. That is let H be anti-canonical class. Then it's self-type. I'll write it just, let's for simplicity write it for, anyway. It's just numbers of rational curves of degree D of degree j minus I plus 1, intersected, general representatives, so I will write H n minus j and H I multiplied by this number multiplied by 1 over degree, anticanonical degree, so h to n, it's the degree. So what's it? You count the rational curves line on our variety given with of given degree, intersection, and so intersecting hyperplane sections, so of bilinear space of condimension, just like this. The example for maybe in this part I'll write example for P2, so for projective, for projective plane we get the following. So we see that we are looking, let us find such matrix for projective plane. we are interested in rational curves of a given degree intersection in two classes. So the only one on projective plane is line passing through 2 points, because it's otherwise it's infinitely many number of curves. So we have 3x3 matrix with all 0 entries, except for this one, which is and the number of line passing through 2 points is 1, but multiplying by some coefficients we get that it's 3, it should be 27. So and that's the usual. Then there is the following procedure. Given this matrix, this counted matrix, we may write down the differential operator of, in just combinatorial particular way. Just let us do it in this case. So the informal sense of this matrix is just a matrix of quantum multiplication by canonical class in basis, just natural basis, degrees of canonical class. For example, for this matrix we get d2, for p2 it's d squared minus 3 cubed. No, it's just t, this formal variable t cubed multiplied by d plus 1 and d plus 2, where d equals t, d over dt is just a coherent derivative. That is our quantum demodule. Anyway, let me and what is this? It's easy to see that solution. Now I want to talk about solution. All these demodules or differential operators have only one analytical solution distinguished, and another ones are just logarithmic. And the solution is, we denoted I P2 in some strange way, but anyway, there's a series 1 plus sum of T2 3k multiplied by 3k factorial divided by k factorial cubed. And actually, and knowledge about, all information about Gromov-Witten invariance, about this quantum demodule and so on, contains in this distinguished solution. So if you know the solution and know the series and know that it's the solution of differential operator of this type, because you can't get any differential operator, then you may reconstruct a differential operator, quantum demodule, and these invariants. And this solution is important for our mirror symmetry conjecture. And the last point I want to talk about this stuff is just remark about all of these are known for so these matrices or quantum D-modules for the complete intersections in in toric varieties or projective spaces. Of course, they usually complete intersection toric variety have greater Picard rank, but anyway, analog threefolds. Intersections, complete intersections in Grassmannians. Maybe generalized Grassmannians of some group, and so on. It's just a lot of examples. That's the so-called A side of mirror symmetry of this type of conjecture describing our variety X. So what should we? So what's the mirror side? Mirror is the following. The mirror for variety for Fano variety is actually not a variety but a pencil of varieties, Calabi-Yau varieties. So a pencil mirror. A pencil of varieties and given such pencil, we may do the following. Let the dimension of its fibers equals k. Then we may associate k fiber-wise k cycle of real dimension k, so middle dimension, and k form of course continuously dependent on the base, and consider the following function. It's just integral of this form over this cycle. So it's just period. And Picard-Fuchs D-module or differential operator associated with our y is just D-module with solutions of this type, with periods as solutions. Solutions of this type. So by definition we say that given our Fano variety X, the pencil given pencil is mirror for our X if, so definition, we have X associate quantum D-module, you know information about curves. We have some pencil and associate D-module Picard-Fuchs. Some questions? and we say that y is mirror for x if these modules are isomorphic. If but in this case, just by definition, we see that we need actually not the whole our pencil, but fibrous open part. So if we cut out some divisor or something like this, nothing changes. So this enables us to, so we may simplify our variety y to be to make something more simple. And the best way known for me is the following. Assume that y is just complex torus. It's to the dimension n capital. It's not so the dimension. By the way, every variety may have several mirror varieties. So, and we call it usually Landau-Ginzburg model. So we may associate several Landau-Ginzburg models with our given variety, and they may have even different dimensions. But in practice, the best, the most correct Landau-Ginzburg models have the same dimension as our variety, but not. So that's why I denoted in the same way. Okay, if our target is just torus, what's the map for? So the map is the function on torus is just Laurent polynomial. Polynomial, and in this case. There is a nice theorem. It's just like mathematical folklore, came from Netherlands, used several times there, but the following. For pencil, just this pencil, and we invert coordinates, so 1 minus tf equals 0. So there is such particular cycle of middle dimension and form such that the function, this integral of this form over this cycle is of the following way type: 1 plus constant term of f multiplied by t plus constant term of f squared multiplied by t squared plus constant term of f cubed multiplied and so on. So that means that in this case we may just we may combinatorially describe this procedure and get in the easy form of a unique analytical solution of our Picard-Fuchs-D module. So that's why our definition is the following. We call, by definition, we call definition number 2. Laurent polynomial f is called weak Landau-Ginzburg model for variety x if the series obtained in the same way for our y, do not here y, equals a unique analytical solution of quantum D module we discussed before. So and in this case, to prove the and plus some conditions on fibers, but the main condition, of course, is this. So in this case, what means to check this mirror symmetry of Hodge structure variations for our variety? If we know it's Gorham-Whitney invariance, we may construct just particular series, particular coefficients, and we need to find a polynomial with this property, the constant terms of its powers equal our given coefficients. And we expect when I'll say just Landau-Ginzburg for homological mirror symmetry, not this, but the first type of mirror symmetry conjecture. We need Landau-Ginzburg model which is fiber-wise complete, but here we have just this polynomial gives us the pencil of open hypersurface in torus. But we expect that compactification, and when I say Landau-Ginzburg model, I just mean that it's what we need for homological mirror symmetry, so fiber-wise complete. And when I say weak Landau-Ginzburg model, then I mean polynomial or pencil given by this polynomial. And we expect that Landau-Ginzburg model, so for homological mirror symmetry, is a compactification in some way of weak Landau-Ginzburg model, so of pencil, our pencil. Or I write of weak one. It's by definition it's polynomial, but I mean the pencil given by this polynomial. And let me just make a few remarks about these polynomials, why they are so interesting. Or maybe before this remark, let us check. So we found that. Let me remind that for P2, what it means for P2. We found that constant term series. This I series are 1 plus sum of t to 3k. 3k is small? Oh, it's okay. Well, I wrote it anyway before. K factorial cubed. And I suggest, well, it's the first example usually when in talks about Landau-Ginzburg models. The weak Landau-Ginzburg model for P2 is just in its polynomial on two variables, x plus y plus 1 over xy. And it's easy to check that this series it's called constant term series. But anyway, we may find this series for this polynomial, and we get that it's just equal to this. It's just easy exercise. So we see that we have the series, so non-zero constant terms will be only at degrees 3k, because to make, we just multiply this, and this. Oh, easy exercise shows that they're equal. So this means that in our definition, this polynomial is weak Landau-Ginzburg model for P2. So return to our remark. Actually, these polynomials have a lot of interesting and deep properties. For example, they are related with toric degenerations, with toric degenerations for our variety X. That is, it's well, conjecture. It seems that Newton polytopes of polynomials corresponding to finite variety X is exactly a polytope corresponding to toric degeneration of X, but it's well, it's known only in some cases. And a lot of another properties, they are not so they are known for as usual complete intersections, finite threefolds, intersections in Grassmannians, but there is no general method how to find them. For finding. it seems to be simple, just combinatorial. You know, some series sequence of numbers, and you need to find just polynomial whose constant terms equals given numbers. But so you may try to find it with indeterminate coefficients or something like this. But for computational reasons, it becomes that it's almost impossible to find it. So one should use some geometrical properties, just like toric degenerations. So one may assume that this relation with toric degenerations holds, and find polynomials with given Newton polyhedra or something like this. So there is no method. So here also they are also known by Batarev, from Batarev, that if our variety X has good toric degeneration for terminal toric variety with terminal Gernshtein singularities, then they are also may be written. So the scheme now I described this mirror symmetry conjecture for Hodge structure variations, and now I want to talk about how to use them for predicting some geometric properties of variety. So if you have questions on this stuff, you maybe ask now, because I changed. No questions yet? Okay, so the scheme of using this approach is the following. We have some funny variety we want to study. Then using all I've told about, we may find sometimes weak Landau-Ginzburg model. So it's more easy than establish homological mirror symmetry. Homological mirror symmetry. Then it's so it's pencil of open of hypersurfaces and torus of open varieties. Then compactified. Maybe later I'll talk about a few words about this, because well, in higher dimension there is no such notion of minimal resolution, or something like this. But anyway, and after compactification, we assume that what we get are Landau-Ginzburg model for homological mirror symmetry. And then this using homological mirror symmetry, we may extract a lot of geometrical data for X. So now I want to give some examples, or maybe a point of compactification. Actually, it's better to think that mirror symmetry is not duality between two varieties, or variety and pencil of varieties, but duality between moduli of varieties and Landau-Ginzburg model, so of x, moduli of x, and one moduli of y. And so what we done here, it's just for all definitions are just for general representatives, the informal meaning for general representatives of general varieties. And actually all of them, so all of varieties from the moduli have the same weak Landau-Ginzburg model, the same polynomial, but the way for compactification this given polynomial to sheaf of pencil of compact varieties, choosing this way for compactification is choosing the type of variety from moduli. So for general variety it will be one way, for some particular variety it will be another way, some degenerated maybe way of compactification, and so on. Just for P2, for example, compactification, it's rigid, but compactification is the following. That's a pencil of elliptic curves. Usually the fiber of Landau-Ginzburg model are Calabi-Yau varieties with 3 singular points corresponding to exceptional collection. And on infinity, that's all, because but on infinity, if you want to compactify, it's a wheel of 9 projective lines. 1, 2, 3, 4, 5, 7, 8, 9. So it's elliptic fibration. That's for P2. Oh, you just compactify this as from 2-dimensional torus to 2-dimensional projective space, and then resolve singularities. But anyway, so what's examples of this, the last arrow, what means exact geometry? Informally, singularities of y correspond to derived category of coherent sheaves of x and exceptional collection. So just for P2, we know that for P2 there is the derived category. It's the derived category of coherent sheaves is just a category of complexes of coherent sheaves modular, and we identify complexes with the same cohomology. That's anyway, if somebody don't know what's it, that's not important, but for those who know, they know that this category has exceptional collection, full exceptional collection containing 3 sheaves. So that's exactly these 3 points. And usually these Landau-Ginzburg models compactified behave in the as the following. There is finite number of single fibers, just like here, which correspond to and one distinguished fiber over zero. Here is nothing special, but usually it's very reducible, contains a lot of components and so on, and fiber of this over zero correspond and monodromy around it correspond to a Hodge structure of X. And just as an example, as an example, we may of this last arrow, we may prove the following theorem. It's just now I'll focus on Fana threefold case. So smooth Fana with Picard number 1. There is 17 families. It was found by Skoskih in 79. And from geometry, for all of them, the rationality questions, so if they are rational or not, it's known. Well, almost known. So for general representatives, it's known. And these weak Landau-Ginzburg models for them are also found. And computing monodromy around this fiber over zero, Goloshev computed it, and comparing the list, we may deduce the following theorem. So it's just easy corollary from Goloshev's calculation and this classification. Of course, complicated, so it's maybe better to write Goloshev is Skoskih. It states the following. Let us have Fana threefold, just one of these 17 families.